Let's be honest. You see that tiny little number floating next to a big one, or that weird checkmark symbol, and for a lot of us, our brain just, well, it just short circuits. It's a feeling so many of us have, even years after we've left a math class. But why? What is it about these symbols?
So let's really dig in. Why do these specific things trip us up so consistently? It's not random. And what's really fascinating is that the answer tells us something pretty fundamental about how all of our brains are wired to learn. Okay, take a look at this. This right here is probably one of the most common ways our intuition leads us astray. Our brain sees a repeated number, and it immediately jumps to a pattern it knows really, really well, adding things together. But an exponent isn't about addition at all. It's a shorthand for multiplying something by itself over and over again. It's a really subtle leap in logic, but it's the very first crack where understanding can start to crumble.
So first, let's just frame the problem. We're talking about what are, arguably, some of the most confusing symbols in all of mathematics. And this is so important to get. If this stuff trips you up, it does not mean you're bad at math. It's all about pattern recognition. See, our brains are literally built to find shortcuts. But when you try to apply those shortcuts to abstract rules you haven't fully grasped yet, you can end up going down the completely wrong path. It's a feature, not a bug, of how we learn. All right, so to untangle this whole mess, we have to go back to square one. Let's get absolutely crystal clear on what these symbols are actually saying. At its very heart, an exponent is just a lazy way to write repeated multiplication. I mean, instead of writing out 3 times 3 times 3 times 3, you just write 3 to the power of 4. It's a shortcut. You could almost call it a piece of mathematical slang. That's really all it is. So the formal definition you see here says it's the power to which a base is raised. In our example, 3 is the base, 4 is the exponent. Simple as that. And then you've got the radical, which is basically the flip side of an exponent. That checkmark symbol, that's the radical. The number tucked inside is the radicand. And see that tiny number in the corner? That's the index, and it's the boss. It tells us which root we're supposed to find. Square root, cube root, whatever it is. Okay, definitions are locked in. Now let's get into the mental traps people fall into. And trust me, this is where it gets really interesting. First up, the even root trap. Your brain looks at the square root of -10 to the 4th power, and it says, oh, easy. The root and the power cancel out, so the answer is -10. Makes perfect sense, right? But here's the trap. With an even root, like a square root, the final answer can't be negative. You have to take the absolute value, which makes it +10. This one little rule trips up just about everyone. But now watch this. This is what makes it so confusing. If we switch to an odd root, like the 5th root of -10 to the 5th, the rules completely change. A negative number can go in and a negative number can come out. That absolute value rule, gone. The answer is -10. Having two totally different rules for even and odd roots is a classic source of confusion. And then you get to fractional exponents. This is where the wires can really get crossed. It's so easy to mix up what the top and bottom numbers do. People often think the denominator, the 2 in this case, is the power. But it's not. It's the index of the root. And the negative sign? That just means flip the whole thing into a fraction. So a to the -7/2 actually becomes 1 over the square root of a to the 7th. And look, this isn't just some small, nagging issue. In her research on this very topic, Feiruz Farah Sarkis found that this specific confusion, the link between radicals and exponents, was the #1 source of mistakes. The, quote, highest frequency. So if you've ever felt totally lost here, you are in very, very good company. So what's the solution? How do we fix this? It's not about just trying harder. It's about fundamentally changing how we learn this stuff in the first place, shifting from just memorizing rules to actually building and understanding. Okay, let's make this real. Forget the abstract symbols for a second and just picture this, a wildfire. At 10 in the morning, it's burning 4 acres. And every single hour, the size of that fire doubles. How would you even begin to model that kind of growth? Well, let's just follow the logic. At the start, hour 0, it's 4 acres. After 1 hour, it's 4 times 2. After 2 hours, it's 4 times 2 times 2, which is, wait a second, just 4 times 2 squared? And right there, just like that, the exponent isn't some arbitrary rule from a textbook. It's a tool. It's a way to describe explosive real-world growth. That little t in the equation becomes a way to see into the future of that fire. And this is a perfect illustration of a huge shift in how math is taught today. The goal isn't to just hand students a list of rules and say, memorize these.
It's about building those rules from the ground up, using real examples. You start with a pattern, and you let the learner discover the rule for themselves. A great example of this is something like a card sorting activity. You give students a bunch of cards with different expressions, like 2 to the 6th, or 4 to the 3rd, or 8 squared, and you just ask them to group the ones that are equal. By physically moving them around and talking about why they match, they start to build those connections in their own head. It's so much more powerful than just reading it in a book. So the whole point is that real understanding is built on strategies like these. It's about taking the math off the page and plugging it into the real world, like we did with the wildfire. It's about playing detective with patterns to discover the rules for yourself. And maybe most important of all, it's about asking that one simple question. Does this answer actually make sense? That's the leap from just calculating to truly reasoning.
And that brings us to the core idea, the single most important takeaway from all of this.
Because, getting the right answer is one thing, but true mastery, the kind of knowledge that actually sticks with you for life, is about understanding why it's the right answer. It's the difference between just following a recipe and actually knowing how to cook.
So let's just bring it all home. Those tricky rules for even and odd roots, they're not random. They're different for a very logical reason. The laws of exponents aren't magic. They're just a direct extension of basic multiplication. Grounding these abstract ideas in real-world models makes them finally click. And the biggest takeaway of all, reasoning your way to an answer is always, always more powerful than just memorizing a rule.
This shift from just memorizing to truly reasoning, that's what makes these intimidating symbols finally click into place. It transforms math from this dry list of rules into a language for describing the world. Which leaves us with a bigger question to chew on. If this kind of thinking is the key to unlocking math, what else can it unlock?